Rubino from Bqit in Vienna.
Yeah.
And so she'll talk to us about secure communication by quantum superimposing insecure channels. Great, thank you.
So thank you for the introduction and thanks for having me here. So during this talk, I would like to present you some recent results that we have obtained in our labs at the University of Vienna. I will also present some further ideas about these results. Indeed, I will present some results and then I will introduce some doubts about them. I will do it on my own, so you can relax. So this result is about secure communication by quantum superimposing insecure channels. What do I mean by this? Suppose, for example, that there is a sender and a receiver, and the sender wants to send some sort of message. But suppose that instead of sending a classical message like a string of bits, it's going to be a quantum message, so some sort of two-level system, okay? Now, suppose, however, that things are not going so well. So, for example, they have some sort of noisy channel in between, 1, 2, or more. Now, the question is there a way to make use of these channels, like to position them in some certain ways so that actually the sender can send as much information as possible to the receiver, can somehow restore some sort of the information that is lost through the noisy channels? The answer is yes, and you can use several different architectures for this. So I'm going to present now within my talk these several different architectures. However, I'm going to first start with some sort of introduction to the topic, so I will just give you some ingredients to understand everything I'm going to present afterwards. So I'm going to present classical Shannon theory and quantum Shannon theory very briefly. Then I'm going to present one possible architecture for these channels. So I'm going to speak about indefinite causal order of these channels. And then I will make use of this concept used before, so Shannon theory and indefinite causal structures, to present a possible architecture for putting these noisy channels. Then I'm going to present you my doubts. And finally, the next steps. So let's start with classical Shannon theory. So Shannon theory is a theory that aims at quantifying fundamental limits in the communication of information. So, for example, I want to send a string of, I don't know, even just classical bits. I want to know, for example, how much I can compress them given the amount of noise that I know being between me and the receiver. Also, these quantities are always usually very strongly related to the amount of entropy in the string. The more entropy there is, for example, the less I can compress it and stuff like this. So every time now I'm going to speak about Shannon entropy, this is going to be strongly related to the amount of entropy in the system. Now, another important quantity in classical Shannon theory is the mutual information. So again, this game is always, I'm here, I want to send information to someone over there. I want to compare the mutual information between what I've sent and what has been received. So how much my information was modified in the process. Okay, but as I was saying before, I want actually to do this game in a quantum scenario. So everything I have introduced so far about classical Shannon theory, I just have to convert to quantum. So how do I convert it? Okay, first, what does it mean to convert it to quantum? It just means that the carriers of information are not anymore classical strings, but they're going to be quantum systems, for example, two-level systems. And can I use the same quantities I just introduced for classical Shannon theory, but for quantum Shannon theory? The answer is yes and no. So for example, the entropy, yes, it's still a fundamental quantity, but in the quantum case, I'm not going to use Shannon entropy. I'm going to use von Neumann entropy, which is pretty much the quantum case of the Shannon entropy. So I'm going to make use of the density matrix associated to my quantum system. Okay, now let's move to the second quantity. So can I use mutual information? The answer is yes, I can, but I would not take into account all the information I can actually have from my quantum system, because the mutual information would not take into account the presence of the coherence terms in my quantum state. So usually, whenever you want to have a full quantum picture, you would actually make use of the so-called coherent information. So, okay, perhaps now I'm going to explain you a little bit what we mean by this quantity in a more practical case. But first, what I want to ask, what I was asking myself since the beginning of the talk was, okay, I said classical Shannon theory, then I said, let's quantize the carriers of information so that I can see if I get advantages. Now I want to do a further step, and I want to say, okay, but how about I do not only quantize the carriers of information, but also the way in which the information is transmitted, so somehow the paths that my carriers of information are undergoing. Do I get further advantages? Now, this was studied recently in a series of works by the group of Giulia Rubino in 2018 and 17. And they show that, yes, there are some intelligent architectures that you can use so that if you quantize both carriers of information and paths, you can actually obtain further advantages than quantizing only the carriers of information. So what type of intelligent architecture I'm referring about? I'm referring about ideas that were developed just recently before this, so around 2012-13, and they are related to indefinite causal orders. So in particular, it was observed that quantum mechanics predicts the existence of processes that are neither causally ordered nor a probabilistic mixture of causally ordered processes. What do I mean by this? So let's do a very easy example. Now, suppose I have a target system, my information, for example, and I want two parties to act on this system, say a party A and a party B. Of course, because I want both of them to act on my system, then one has to act first and the other second. So if I want to do this decision, if I want to take the decision of who acts first classically, I could, for example, flip a coin and say, okay, whenever I get head, A is going to act first. Whenever I get tail, B is going to act first. If I play the game in a quantum fashion, then I could use, instead of a coin, a two-level system. And so I could say, okay, let's say I have a target system that I send to A and B, and a control system that decides who gets it first. If my control system is in the state 0, then A gets it first. If it's in the state 1, then B gets it first. But again, I said I am using now a two-level system, two-level quantum system, so also quantum superposition of the two are allowed. And so, for example, I can have cases like 0 plus 1. So cases in which both A and B receive it first in a quantum superposition. So this is a so-called quantum switch. In general, an N switch is just a quantum superposition of all the possible permutation of N gates. And we call quantum switch the case for N equal to 2. So during my talk, I'm going to focus just on a quantum switch, so only on the case for N equal to 2. But of course, the same story can be generalized to more channels, more A, B, C, and D, and so on. OK, so this is pretty much all what you need to know for understanding this talk. And furthermore, you might want to remember the concept of Krauss operators. And now let's apply this concept I have introduced so far to the advantage I was introducing at the beginning in terms of quantum communication. So we consider this quantum particle experiencing this channel A and B. I call my quantum particle target qubit, and I want to put it in a quantum switch. So I will have my target qubit that is together with another in a composite system with a control qubit, and whenever the control qubit is in the state 0, then it's going to pass through a channel A first and then a channel B, while whenever it's in the state, the control qubit is in the state 1, then the target qubit is going to pass through B and then A. Okay? Now, yeah, this is just, if you want to write in terms of Krauss operators, you can write it in this form, and this is the form in which we write usually the quantum switch. Now, I want to show you that if I have these two noisy channels and I put them in a configuration like the quantum switch, I can actually achieve this better transmission that I was speaking about at the beginning. So the sender is able to reach until the receiver with a higher amount of information than if it just was going normally through these channels. So as I said, the two quantities I'm going to use are just these two, so von Neumann entropy and coherent information. And in particular, I'm going to use them to quantify the so-called channel capacity. So how much capacity has my channel ability to transfer this amount of information. So let's do a concrete example. So this is the formula I will use, and now I explain you what it means. So as I was saying, I have my quantum system. It passes through some noisy channels, A and B. Okay. Now, I don't really care of what these noisy channels are. It can be just a big noisy channel N. And I'm going to call my input state alpha and my final state omega. Of course, this could be the same if the channel is adding zero noise, or it could be something very different. And then I consider a further ancillary qubit alpha prime that doesn't pass through the noisy channel. So alpha prime, of course, is going to stay alpha prime because it just passed through unaffected. Now, I can quantify the channel capacity of this big channel N with this formula, where I have that the max is over all possible states of alpha and alpha prime. So they could be mixed states or entangled states, whatever. And I calculate the difference between the von Neumann entropy of just the output state and the joint output state of the output state and the ancillary qubit. Now, again, I just want to give you an intuition of why this works. So let's consider the two opposite cases. So let's consider the case in which I start with a maximally entangled state and a case in which I start with a mixed state. So for now, we keep our noisy channel off. So the noisy channel is doing nothing. Whatever you insert is going to get out. If I send a mixed state, I have nothing to lose in principle. So as you can see, you will have that the entropy of omega is just the entropy of a mixed state, and the entropy of the final state, of the final joint state, is just, again, the entropy of a joint state, but bigger Hilbert space. And so you will have that this minus this, of course, is a negative quantity. Instead, if you have an entangled state, then you will have that the entropy of this is still a positive quantity, but the entropy of the final state is 0. And therefore, you will have that this difference is bigger than 0. Now, so far, my channel was off. So if you suppose that I start from an entangled state, but I switch on my channel, all the channel is going to do is going basically from this case to this case somehow gradually. And this allows me to get the information about the coherent, so the capacity of my channel. So this is just a very end wavy idea. Of course, like there are many more cases and analyses, but this is just to show you roughly how this formula works. Okay, so what did we do actually in the lab? So we implemented this with a quantum optics setup. In particular, as I was saying before, we need two qubits. We had, you remember, this alpha and alpha prime, and we need them to be entangled. So first, I built an entangled single photon source. I did this just with an SPDC type 2 process. So I had a laser pumping a BBO type 2 and generating single photons, which were entangled in polarization. I corrected, of course, the, like I make them degenerate using filters, and I correcting spatial and temporal walk-off with compensation BBOs. But besides from all this, basically, I pretty much at these two couplers, I know that I have two entangled photons. Then I send one coupler to my noisy channels, and the other coupler to just a measurement, because as I was saying before, alpha prime is going to be unaffected. Okay, then so my alpha is going to get inside this so-called quantum switch, and in particular, is going to go through this first beam splitter. So as I was saying, the entanglement is in polarization, and I'm going to implement the control qubit in the path degree of freedom. So I'm going to perform a superposition of two paths, and like whenever the photon is transmitted, then it will undergo the operation of a channel A and then of a channel B, and vice versa when it's reflected at channel B and then in channel A, and then it's recollected on a second beam splitter that cancels the which path information, and then I'm going to measure it as much as I do with the ancillary qubit. Okay, how do I implement the noisy channels, A and B? I implement them with some liquid crystals. Liquid crystals are pretty much, you can, for whoever of you has never used liquid crystals, they are pretty much like some wave plates, but way faster. Like you can implement operations with, say, for example, tens of microseconds. So how do I use these liquid crystals to implement some noisy channels? The idea is the following. Let's take an example. For example, let's consider a bbeautiful channel. A bbeautiful channel is a channel of this form, so it has the contribution of the identity operator and all possible Pauli operators. What I'm going to do is the following. I first generate two random numbers, say P1 and P2. Then I set this probability P, that is the one determining my channel. And then, for example, if both P1 and P2 are bigger than P, then I will implement the identity. If P1 is smaller and P2 is bigger, then I will implement sigma Z. If one is bigger, one is smaller, sigma X, and if both are smaller, sigma Y. Then I iterate this many times. So that's why I wanted to use some liquid crystals so that they are very fast, and I just can keep my detectors on, and I keep on integrating over time. And yeah, of course, I will observe that the more iterations I do, the better I approximate a noisy channel. For example, we observed that still for 100 iterations, it was pretty bad. But then, like the more you scale in terms of order of magnitude, so if you do 1,000, it gets way better. If you do 10,000, it gets even better. And in the end, you really very well approximate already for 1,000 a noisy channel of this form. Okay, so for a noisy channel of this form, you obtain that if you have just your quantum information going through the two channels A and then B, just say, so two bbeautiful channels one after another, you will have that the coherent information is going to be this one. So the amount of information that you actually transfer, depending on P, which was this value that I was saying in the formula before, is this blue one. If you want to put it in an architecture like the quantum switch, you partially have some advantages only in a limited region. So only basically, you see, wherever this red line is above the blue line, then we actually have an advantage with respect to the standard order case. And yeah, these are the experimental data. So as you can see, they verify quite well the theoretical trend. So this is one channel. Of course, it's not amazing. Like you can see that, okay, it's only a very limited region, the region in which you have the advantage, but still you can get an advantage. Now, there are other channels where you can actually get better performances. For example, for the entanglement breaking channel, this is just a superposition of Pauli X and Y operators. And the principle in which we implement it is just exactly the same. We will have two probabilities and always generate random numbers and so on. For this, you will observe that actually you can, with the switch, you can restore the information fully. So you can actually get 1. And so, for example, for a probability P equal to 1/2, you will see the best advantage in using this type of architecture instead of just going the channels A and then B. Okay, then we observed also a further channel. So far I always consider the case in which I only have the 2 times the same channel, so A and B are just 2 bbeautiful or 2 entanglement breaking. We also consider case in which we have 2 different channels. So for example, A is a bit flip and B is a phase flip. And we observed also in that case an advantage for some certain areas of the probabilities. Just to be complete, we are not the only one who have verified these trends. These same experiments were also carried out at the University of Brisbane by Professor White, and also in China by Guang Kangguo and his group. So this is the verification of the advantages with the quantum switch. Now the part of the doubts. I said we can put them in a smart configuration so that I can obtain actually a higher amount of transmission of information. Now, I just automatically presented you the switch and I said, for example, this is an intelligent architecture. But now the question is this the only one? Like, can I find other architectures that are as well performing, better performing, or stuff like this? For example, in October, the group of Cyril Bransiard proposed that this is not the only architecture. So if you have A and B, and you have to pass through them, but you want to try to restore part of the information, they show that actually you can do it also just putting only A and B in quantum superposition. This is also going to give an advantage. And so for this reason, they thought, okay, perhaps causal order is not actually needed to observe this type of advantages. However, a couple of days after, the group of Giulio Cribella showed that actually this is not always the case. For example, they presented here this entanglement breaking channel that I was showing you before, and they showed that for the entanglement breaking channel, the scheme proposed by Cyril and his group is not actually working. So they showed that actually, no, it really seems like you need indefinite causal structures to obtain this advantage. Okay, so we perhaps agree that we need superposition of channels, of twice the same channel or stuff like this. But how about different causal orders? So, for example, I mean, there are only two ways of superimposing causal order between two channels, right? Either you switch the order or you don't. So if you switch the order, you get the advantage. How about we don't switch the order? Of course, to not switch the order, I need to add some sort of preprocessing, some pre-gates. Otherwise, it would just be trivial if I just superimpose AB and AB. So I add some pre-processing before, some pre-gates, D and W. Do I obtain an advantage? Now, from the experimental point of view, we think there is no reason to actually consider one scheme and not another, because the scheme I was presenting you before, it's pretty much a Mach-Zehnder with two loops. The scheme to implement this superposition of same orders is it's just a Mach-Zehnder with no loops. So in terms of resources, like experimental resources, you need the same amount of resources. So can I use this type of schemes to obtain similar advantages or better or worse advantages? The answer is yes. And for example, for the case of the entanglement breaking, we just get, of course, we were already getting the best with the switch, so we cannot get any better. So we just get the same. We get the best. Like, it's not super visible, but it's this yellow dashed line over here. So all these results I'm going to present in this very moment are just theoretical results because I'm still performing them in the lab, but these are our predictions. So yeah, for the case of the fixed order circuit, so the superposition of same orders, you see that you actually obtain the same advantages. I'm also going to explain you very, very shortly why this actually works. So in the case of the switch, it was shown that you have that if you have these two gates, for example, the output of the switch allows you to calculate properties of commutation and anti-commutation between these two operators. So you get basically an outcome of this form. So basically what you're going to have is that with probability 1 minus p squared, A and B are both sigma x. And so they are the same operators, so they commute. So this term is 0. They are just going to be basically the identity because it's twice the same operator, Pauli operator. And so you're going to get this as an outcome. So pretty much you get psi as an outcome. If instead, same of course if you have two sigma y. If instead you have a sigma x and a sigma y, then you are going to have that the anti-commutator is 0 and the commutator gives rise to just a sigma z. So you know you perform a sigma z on your output state and you restore fully the information. So for what concerns the switch, this is the reason why it works. Why does it work for our case? For our case, for example, to get this best advantage that I was showing you before, we can get it just making use of a first preprocessing. So we have a sigma x. And then in one case, when the control qubit is 0, we just go through A and then B. And when it's 1, we go through sigma x, A, and then B. In a circuital form, this can be written in this way. And it works because if you recall even just protocols for error corrections and stuff like this, if you have a first C naught, you can basically transfer the information from your target to your control qubit. And then all what you do is you're going to apply twice this channel. So basically it's somehow like applying either twice a sigma x, which gives identity, twice a sigma y, which gives identity, or mixed once, which gives sigma z. And so the most you do is either implementing an identity or implementing a bit flip in the target qubit. And so basically all you're going to obtain is that either you have this with a plus or with a minus. But either you get this with a plus or with a minus, but you don't really care. Once you measure the target qubit, if you see 0, you know that the control qubit is exactly what you wanted to transfer. If you see 1, you're just going to implement a sigma z on your control qubit, and then you got what you wanted to transfer. So this is an easy example of why this works for the entanglement breaking case, in which, as I said, they just perform as good switch and superposition of same orders. How about the other channels? So for the bbeautiful channel, we saw that actually do not making use of indefinite causal structures performs better. So it's better to superimpose them, but keeping the same order, than to superimpose them, switching the order, having AB and BA. So as you can see, this is the yellow line, and yeah, it's above everywhere with respect to the switch. So it's not really convenient to put them in opposite order, but it's actually more convenient to put them in same order and do some sort of small pre-processing. Also for the defacing channel, it's the same. So as you can see, this dashed line is the line with the sigma x at the beginning. And yeah, also in this case, I'm always above the switch, which is the blue line. In particular, if I make use of this, because now I was speaking about only using the gate B, and I was showing you the dashed line. But if I allow to also use another pre-processing W, I get even better results. I get this yellow line over here. So I'm always performing better than the switch. And yeah, this is just because, of course, I have two different channels. So whenever I have that they are the same channel, the only thing I need is to do a pre-processing at the very beginning. If they are two different channels, I do a pre-processing before the first and then a pre-processing before the second one. So yeah, we have actually observed that you don't even need to do a pre-processing only on one. You can just do an Hadamard on both of them, and you get even better results. So, I mean, as you might have noticed at the beginning of my talk, this is a study that we are doing in collaboration also with the group of Kiribella. So we have discussed with him quite a lot, like whether we should actually attribute this sort of advantages to indefinite causal structures or not, and just attribute them, for example, to superposition of paths. And I think it's still a controversial topic because for example, one of the ideas that Giulia raised is that actually in second quantized Shannon theory, you are quantizing also not only the carrier of information, but also the paths. But you do not want to completely transfer the information on the path. Otherwise, you will be just avoiding the channels. And so, I mean, sure, you can restore fully the information. You are just avoiding them. And this is true on one hand, but on the other hand, I mean, once I anyway quantize the other degree of freedom, then why not to use it fully and to transfer the information fully on the other one? So this is one possible, argument, pro or against the use of this superposition of same order. So in line of this argument, you have this no signaling condition. So you don't want to signal to your control qubit. However, we were discussing that anyways, also in the switch, if you have time resolving, you actually do have signaling, because within the switch, like if you can resolve over time, you will observe that in one case you went through the channel A, in the other case you went first to the channel B. So you also can actually discriminate in which state of the control qubit you have. So also this idea of the no signaling, actually it's not very well defined for the case of the switch, and it cannot actually be used to discriminate one case or another. So this is just to say that, so we believe that there are some advantages, yet we are not sure what they can actually be related to. But the good news is this actually gave us the opportunity to learn more also from the fundamental side about these causal orders. Indeed, at the very beginning, the first formulation of indefinite causal order was always in terms of intervention. So A and B were always, some people like Alice and Bob, and they were actually implementing some operations. So they were doing some intervention inside our switch. And so it made sense to speak about causal order between them. But in this case I've spoken so far, they are just channels. They are just defined at the beginning and they are staying there. So this might be a reason why we don't actually observe any advantage with this scheme, because they cannot be defined in terms of intervention. They are just there and they're just staying as they are until the end. So this is also for us an interesting, still open question and kind of research line that we are taking as next step, take-home message from this experiment. And with this I would like to thank you for your attention.
Thank you very much. Do we have any questions?
Hey, thank you very much for the talk. It's very interesting. I'm a bit confused. So in the switch, you have you're controlling the order of A and B based on a qubit, but then in the state of a qubit. But then I didn't see in the optics experiment where the control qubit was.
I mean, I maybe say it fast. The control qubit is the path. I'm getting there.
So control qubit is the path.
So the target qubit is the polarization. The control qubit is the path. And I just use a beam splitter which performs the analog of an Hadamard gate on the path, so that I put the path, so the control qubit, in a quantum superposition of being both transmitted and reflected, and therefore of being in the two orders.
Sure. Okay. Thank you.
Someone's just coming.
So thanks for the talk. I don't know so much about causality, so maybe I like something not so refined, but you commented that you can generalize some of the results to more general causal, not causally order structures. What is known about process matrices in general? Like, can you say something about that?
Yeah, no, I didn't speak about process matrices because I spoke all in terms of Krauss operators, but of course everything I said so far can also be translated in the language of process matrices. In particular, so what I was referring to when I said that sentence that this can be generalized to more parties, I just referred to the fact that you can also have superposition of not only A and B, but you say A, B, C, and stuff like this, so all the different permutation between also these three gates. And of course, this is fully formalized also in the process matrix formalism. The process matrix formalism is just an analog formalism to the one I introduced here, which makes use of the Choi-Minkowski isomorphism, and you just present all the gates applied as some sort of tensor product between the black boxes of the, like preparation of the input state, measurement of A, measurement of B, and detection operation. And then you just do, basically, you describe everything in terms of process matrix, which describes somehow the way in which the information is transmitted between the parties. So not really the state of your qubit, but just, as I said, the process, the causal process. But you can describe 2 parties, 3 parties, every sort of party with process matrices.
Most works focus on the switch so far, right? Most of these works.
Experimentally?
Yeah.
So only for, so far the switch was done only with photons, yeah.
So if there are no other questions, then let's thank Giulia once again.